Okay, this is section 3.5, and today we're going to take kind of all the solving we have been doing with exponentials, and we are going to do a bunch of word problems, which has got to be your about favorite thing to do in math. And most of our word problems are going to be based off this growth model or a decay model where exponents are concerned. So growth model, we've talked about them in and actually have graphed them, and they are where the exponential function just quickly increases. And that mainly happens because your b, your growth rate, or your r as we were using it, is positive. So as long as your growth rate is positive, you're going to be increasing exponentially. And our equation is very reminiscent of p to the e to the rt. They are the same formula, just different letters used, but they give you the same results and they're used in the same way. The decay model is one that we haven't really talked about. Although we graphed it, we definitely got to look at it. And decay models look like this. They just quickly decrease. And that just means that the rate, or your b, is negative. So anytime you are decreasing. Now exponential models we have used a bunch of different times, usually just solving them. In word problems, they would be related to maybe like population of a city growing exponentially, or bacteria in a petri dish growing exponentially. Decay models, the examples that we use kind of focus around something called a half-life, when isotopes or radioactive material kind of decays over time. So that's what we're going to use for our reference in our word problems. So growth and decay, same setup for an equation. They stand for and mean the same thing. A is your initial amount, E is our 2.7, our number, constant, and then b is our rate and x is our time. So they are the same setup as p to the rt that we were doing with money just a couple short units or lessons ago. So first one says, how long would it take for an investment to double if the interest were compounded continuously? So seeing that compound continuously means I'm using the pe to the rt, and I'm trying to figure out how much I will have on the account. They gave me a rate, which I'm going to turn into a decimal, so it's going to be pe to the 0.08 t. It said how long, so t is what I'm solving for, and then usually students get a little hung up with, well, I don't know how much I'm investing, and I'm like, well, actually, here to blow your mind a little bit, it doesn't matter if you invest $10 or $10,000, the amount of time to double will be the same. If you're investing $10, your returns will be very small, just pennies. If you're investing $10,000, you'll probably get, maybe tens of dollars or maybe hundreds of dollars in interest. And so the rate at which you double is still this 0.08, no matter how much money you had to start with. So the amount of money actually is kind of immaterial. It doesn't really matter to us how much money you had. But whatever it is, you would just like to double it. In the end, you would like to take your initial investment and double it, turn it into 2p. And right away, I'm just going to divide by p to get rid of that. That's why it even becomes more clear that I didn't need to know my initial amount. All I needed to know was in the end, I wanted it to double. So I have that 2 on the other side. So 2 equals e to the 0.08t, and at this stage we can ln both sides to get rid of that e. So I've got the ln of 2, which is just a decimal for us. And then I will be dividing. I'm going to write 0.69, but I don't want you to round that much. I want you to use this whole number, and I'm going to show you how to do that. 0.08t. So the last step I would do is divide by 0.08. And I'm just going to hit the divide button so that it uses all of that answer. So I don't just use 0.69 because that'll round my answer way too much. I want to use the whole thing. And it looks like this is going to be about 8.66 years. So no matter how much money I have to invest, if I have an 8% interest compound continuously, it's going to take me about a little over 8.5 years to double my investment. Next up, I've got $50,000 to invest, and I need to have $350 to retire in 30 years. So now I've got a good goal here, kind of real life. What percent would you need to get in order to reach your goal? So I have my $50,000 that's going in for initial investment, or my initial amount. E to the r, I don't know. That's what we're trying to find out, is what would the rate need to be. And we have 30 years to sit on this money, and we need it to turn into $350,000. So first up, I'm going to divide by the 50,000. End up with 7 over here, e to the r times 30. And it looks like it's like so many other problems we've done, we're going to ln both sides. So I'm going to have the ln of 7. Cancels that e. So I have about 1.94. Again, I don't want you, I'm just writing this number down, but I want the whole thing. So don't be rounding that. and then that's going to equal 30r, or r times 30. Last step will be to divide by 30. So I'm just going to hit divide by 30, and that's the decimal that I want. So my rate ended up being 0.0648. I'll do 4 decimal places. And remember that when we do rates, this right now is a decimal, but we want it as a percentage. Like you would walk into the bank and ask for this particular percentage. The percentage is not 0.06. That's just what we solved for. So our actual percentage rate is, and we'd have to move that over 2 places, so 6.486%. That's the rate we would need to get in order to reach our goal in 30 years. Next up, the population of a particular city in millions can be modeled by this equation. It's still just PE to the RT. So still my initial amount, that's my rate. So I'm getting some information built into the equation. Where x equals 0 corresponds to 1990. So what I do with students when you have something like that is I kind of make like a timeline. So at 1990, that's where our population, that's like where we're choosing to kind of base all of our data off. So in 1990, I had a population of 1.8 million people. That's not 1.8 people, that's 1.8 million people. I would like to know what year this city will reach 2.5. So when will they reach 2.5 million people? That's what I'm trying to figure out. So I'm going to use this equation that they gave me. That's my initial. This is P to the RT, initial amount, and then I have my rate up there. And I just want this all to equal 2.5. So it's almost like saying this is the money I have. I'd like to invest it at 0.02 or 2%. And then tell me when I will make $2.5 million on my initial investment. So I'm going to divide by 1.8. So I've got 2.5 divided by 1.8. So I've got 1.38 repeating. And now we're going to ln both sides. So the ln of that, and I'm using my second answer button so that I use that whole answer and not just 1.38. So 0.328, and I'm going to divide by that 0.02, again using the second answer button, or just hitting divide by and then 0.02 so that I use the whole decimal. So it looks like 16.43, we'll say. That's how many years it's going to take in order for us to get this population of the city up to 2.5 million. So that means I need to add 16.43 years. So the year, what year will it be? It will be the year 2006. One more to go, and this will kind of be the basis of most of the problems that you're going to see. You're going to get a little less information and kind of have to build 2 equations in order to solve it. So there is this radioactive isotope out there called Ra-226. That is not a part of the problem in terms of you're not going to plug in 226 anywhere. That was just me describing the isotope to you. Okay, so it's just me telling you where it is on the periodic table. It has a half-life of 1,620 years. So what that means is like carbon dating, when they dig up a fossil and they find it way out here in the year 2023 or whatever year it is now, they backdate that. They figure out how much of this isotope would have been around initially. And that's how they can figure out how old the fossil is. So what this half-life is saying is, let's just say, so this original amount we had was 5 grams. Let's just say there was 5 of it in this bone or this object. After 1,620 years, that's our starting year. After 1,620 years, half of it will remain. Like it breaks down at that rate. So after 1,620 years, the amount that you have is actually cut in half. Sorry, I just feel like that is not in focus very well. Another 1,620 years go by, so 3,240 years have gone by, and I have half of that remaining. So every 1,620 years, I'm getting, the amount that I had is getting cut in half, cut in half, cut in half. I would like to know how much will remain after 10,000 years. So I could kind of keep doing this pattern, see how close I can get to 10,000, maybe doing some guessing and checking, but we can actually solve it a little bit faster. So looking through my numbers, I've got 1,620 years, that's a time, so I want to make sure I label that. The original amount, so that's P, that's like my starting amount. And how much will remain after 10,000 years? That is another T. So here I am with 2 T's, but in my formula, PE to the RT, I only have 1 T. So I need 2 whole equations, 2 separate equations in order to solve this problem. So I first want to start with my 1,620. We want to start with the half-life and use that to figure out some more data. Learning the half-life is actually like winning 2 parts of your equation. It means that no matter how much I have, I will end up with half of it when that 1,620 years go by. I know that we have 5 this time, so I have half of 5, or 2.5. And so when I divide by 5 right away, I have a half, which is the whole point of half-life. Right up here would have been the same thing. I don't have to know how much I have. If I have 100, then I have 50, and that's half of what I started with. So the whole point is once you are using the years of a half-life, you have half on the other side, because that's what it's doing every time. So we'll solve this like normal. I'll ln that. So I'm going to have ln of 0.5, and then the e is gone, and I'm going to divide by the 1620. So it looks like my growth rate is a negative number, so that's a decay, which is actually true because I'm cutting in half. I'm losing amount after so many years, so that definitely needs to be negative. What you need to watch out for is anything at the back end. So this means scientific notation times 10 to the negative 4th. So I'm moving this decimal place to the left 4 times. So instead of my rate being negative 4%, it's actually negative 0.1234278. And that's a much different rate than 4%. Now I'm going to use that in a whole nother equation with my other amount of time. So A equals PE to the R, and now I have 10,000. I also know my R, so I can put that in there. I'll just arrow it because I don't want to write all that. Times my 10,000. And you know your P, so I'm going to sneak that in and make that a 5. And now we're trying to figure out how much will remain, so this is kind of what I'm solving for, after those 10,000 years. And this I can just plug straight into my calculator. So 5e to the, and I need this answer, so I'm going to, you can either go up there, hit enter, it'll bring it down, or you can hit second answer, and I'm going to times by my 10,000 years. So it looks like after those 10,000 years go by, I'm going to have 0.069 grams remaining of my original sample. Most of the problems that you're going to do are going to be a 2-parter like this. So you're going to end up using some data that we give you. Sometimes it's a half-life and a years. Sometimes it's maybe, you know, after 5 years you have this, or 5 hours you have this much bacteria. So you're going to find your growth rate or your decay rate, and then you're going to use it in a second equation with like the data you're looking for in order to solve the problem.